All right, in this video, we're going to be going over centroids and distributed loads. Let me just make sure. Okay. So yeah, we're going to be going over centroids and distributed loads. Remember, a centroid is the center of an area, right? So you've probably heard like center of mass before, center of gravity. Centroid is the same kind of concept. It's just the center of area, right? So basically you're given this table. You're not given the purple text, but you're given all of these headings in your data sheet. So this is what you're given in the data sheet, or the reference card, I'm sorry. And basically the principle is you'll be given some shape. And I believe the shape you were given on the worksheet, like the practice worksheet, was some sort of shape like this, right? Where essentially the rectangle itself was the positive area, but these were both cutouts. So the triangle and the circle, or the quarter circle, were cutouts. And it basically said find the location of the center of area of this shape, right? So basically it told you something like this will be, we'll call it 12, we'll call this 6, we'll call this 6, this 3, and this 3, right? So something like that. And then it says find the center of area, or find the centroid of this shape, right? So basically, we're just going to kind of work through this example explaining the table, because if you understand the table, you can understand how to solve it, right? So we want to find some center of area, knowing that this is laying against the y-axis and this is laying against the x-axis. So in other words, this is the origin. Okay, so the first column is to find the shapes that combine to form this composite body. So when you're filling out the left column, it's basically just like a list to remind yourself of where everything is, right? So what shapes you have to keep considering. So in this case, it's a larger body is a rectangle. So there's a rectangle. So you physically just draw the rectangle here. And then that's a positive area. So I usually put a little bit of like a plus sign in there. The triangle is a negative area that's cut out. So I'm just going to put a negative. And then the last one is this quarter circle, and that's negative again. So that's really all you put in that column. And then in the second column, it's the area column. So just like you would think, it's the area of that shape. So if I'm looking at the rectangle, it's 12 by 6, which is 72. Oh, wait, I should probably put units here. So it's 12 by 6, which is 72 square inches. And then the triangle is 6 by 3, which is, the area would be base times height divided by 2. So 6 times 3 is 18, divided by 2 is 9 square inches. And then the circle here, the area would be pi r squared divided by 4, right? Because it's just a quarter of the rectangle. So pi times 9, because 3 squared, divided by 4. So 9 pi over 4 square inches. Okay, and then the next thing for you to definitely consider is what area is positive and what's negative, right? So here, this is a cutout, so that's negative and that's negative. That's super important. Once you finish this column, you just sum the areas, and there you go. So then you move into x tilde, right? And x tilde is going to be one of your dimensions that helps you find the area about the y-axis, or I'm sorry, the moment about the y-axis. So knowing that moment is a force times a perpendicular distance, right? I know that I'm going to be looking for the distance in this direction, right? How far it is from the y-axis, because my is the distance, or is the moment about the y-axis. So my perpendicular distance will be measured from the y-axis. So looking at each of my shapes, the rectangle, the centroid is right in the center, right? So that would be at exactly 6, because it's half of the total length, which is 12. So that's just 6 inches. And again, measuring it from here, oh no, measuring it from here, that is still 6 inches because the square is laid up against that, or the rectangle. Moving on to the triangle, the centroid is 1/3 of the dimension from the right angle. So here's the right angle, right? And so it's 1/3 of this distance for x tilde away from the right angle. So 1/3 of the distance would be 2 inches, right? Because 6 divided by 3 is 2. And it's 2 from here. So it's somewhere like here, where this distance is 2 inches. But remember, we're not measuring it from this side. We're measuring it from the y-axis. So I don't really want the 2 inches. I want from here to here, knowing that it's all but 2 inches. So because I'm able to find the distance from the right angle, I know that it's actually 10 inches, because it's the whole 12 minus the 2 that's left over. So this would be 10 inches. And then this one here, the equation for the circle would be 4r over 3 pi from the center, so from this right angle. So the equation for a quarter circle is always 4r over 3 pi. And here r is 3 inches, so it's 4r over, so 4 times 3 over 3 pi, so it's just 4 over pi. And then because, again, this is measured from the y-axis, that's still just 4 over pi inches. So remember, the important part of this column, this x tilde column, and also the y tilde column, is that people will always forget to measure it from the y-axis. So a super common mistake, and really the only part where it comes into play in this problem, is instead of calling this 10, you call it 2. But if it was 2, it would be somewhere over here, which is not the case. It's over here. So that's super important, because a lot of people are going to mess that up. So looking at the y values, right? Y tilde is going to be measured from here, right? Because y tilde is the moment about the x-axis, right? This is given. It's the moment about the x-axis, so you measure it away from the x-axis, so it would essentially be your y coordinate, right? So again, the rectangle itself is just half of the length, so it would be half of this 6, so it would be 3. Let me make them red. So it would be 3, again, because you're measuring it from here, that's still 3. The triangle is still 1/3 of that side length, but now you're looking at this side because that's the vertical distance, that's the distance on the y-axis. And so 1/3 of 3 is 1, measured from the right angle. So 1 is actually right here. But again, because we want it measured from the x-axis, we're going to do 6 from here minus that 1, because we want this distance. So that's just going to be 5 inches here. And then again, this one is 4r over 3 pi, and r is 3, so it's just 4 over pi again. So with these, remember that you always want to measure it from the axis. That's the part where people make mistakes. And then for the other two columns, all you do is you multiply, it tells you, you multiply the value you got for x tilde times the area. So here it would be 6 times 72. Here it would be 10 times -9. And then here it would be 4 over pi times 9 over 4 pi. Nope, 9 pi over 4. So actually that cancels really nicely. Can't believe that. So this one is -90. This one's also negative. Shoot. So pi's cancel, 4's cancel. This is just -9. And then 6 times 72. My brain is not quick enough for that. So 72 times 6 is 432. So, and then what would the units of that be? So I'm doing area, which is inches squared, times this, which is just inches. So the area or the units in this column are going to be your distance cubed. So this would be 432 inches cubed, -90 inches cubed, and -9 inches cubed. And then again, you go down here and you sum all of them. That's the sum of the moments about the y-axis. And then for this one, you do the same thing. So it's the y tilde that you got times the area. So then it would be 3 times 72. And then it would be 5 times -9. So -45. And then it would be the same thing. So it was just 4 over pi times -9 pi over 4. So then that would just be -9. And then 3 times 72 is 216. And then again, these are all inches cubed, because you have inches times inches squared. All right, and then lastly, you sum these, and you get some of the moments about the x-axis. So the question is going to ask you, find the location of the centroid. So really at this point, you haven't done that yet. So what you're going to end up doing is, if you look at your reference card, it gives you the equations for all these. So x tilde is the moment about the y-axis divided by the area, or x tilde times a divided by the areas. So going back over to here, if I look at the x value of my centroid, so centroid location equals, so you basically write it as x bar, y bar, right? That's like the format for it. But that's equal to the sum of the moments about the y column times the sum of the area column, comma, sum of the moments about the x over sum of the area. So if I look back up here, my sum, oh, I should actually solve these, huh? So 72 minus 9 minus, hold on. Well, I'll just leave it as that. So this one is 63 minus 9 pi over 4. That's the whole sum of the area column. This is 432 minus 90 minus 9. So that's 333. And then here it's 216 minus 45 minus 9. And that's 162. So if I come back down here and start filling out this formula, what I get is some of the moments about the y. So 333 over 63 minus 9 pi over 4. And then comma 162 over 63 minus 9 pi over 4. And then what you'll end up doing is, in real life, like on an exam or a quiz, work this out in a calculator so that this denominator is simplified all the way. And then draw on your rectangle where you think it should be. So in reality, I think logically it should be somewhere fairly close to the center. So I think personally it'll be somewhere around here. But that's that. So in or on a quiz or something, make sure you're looking at that. So quickly going through distributed loads, because that's really why we're looking at that. The idea behind distributed loads is that you can ultimately make, from a practical perspective, you can ultimately kind of make a load lighter by distributing it, right? Effectively lighter. So if I have something like this, where, first of all, a distributed load will look like this, where it's like a bar with a bunch of little arrows coming down from it. So that's my distributed load, and I'm given that it's 10 newtons per meter, right? Over a span of, we'll say, 5 meters. Okay, so basically, if I'm trying to solve a free body diagram problem, right, where I have to, like, or like an equilibrium problem where I'm using a free body diagram, I can't solve that as it is right now, right? Because regardless of what other information I have, like I can say, okay, yeah, that goes there and there, and then that goes there, so all of these supports will go away. But what still is there is that I have this distributed load, and if I need to solve a moment equation, then how do I do that? So the premise is, okay, so if I can simplify that to a point load, then I can solve it, right? Because ultimately, a distributed load is equivalent to a point load, or just one single arrow. So that's a distributed load. A point load would look like that. A point load acting on the centroid of the distributed load. And that centroid, because this one is shaped like a rectangle, that centroid is going to act right at the center of the rectangle, because that's where the centroid is. What's the magnitude going to be? Well, I have my distributed load as newtons per meter, and I know a force is supposed to be in newtons, and I know that this force acts over a span of 5 meters. So if I need to multiply the magnitude of the distributed load by some distance to get it to a point load, I would multiply the magnitude that it gave me of the distributed load by the distance it gave me that it's acting on. So this would be a point load of 50 newtons acting at the centroid. So another common one is a triangular distributed load. So if you have something like this, then what do? Same logic, it's a point load acting at the centroid of that shape. Here it's a triangle, so I know the centroid is going to be 1/3 of, wait, here I'll say this is 10 newtons per meter acting over another span. I'll call this 6 meters just so the math looks nice. So it's 60 newtons, right? Because I know I have to do this times this to get the magnitude of the point load. But where is it acting? It's acting at the centroid of this triangle. And if you remember from up here, the centroid of the triangle is 1/3 of the length away from the 90-degree angle. So it would be somewhere around here, where this distance is 2 meters. Because here's where my 90-degree angle would be. The entire length is 6. It's 1/3 of that, so it's 2. And then we know that this is 60 newtons because it's the distributed load magnitude over the distance it's applied. So this usually comes in when you're trying to solve equilibrium problems. In this case, it'll probably come in mostly in frames. So that's why we end up teaching you the centroids lesson. All right, so I will stop this and record the rest of them right now.